Yep. So I'm going to talk about the DeepQ networks, and this is presented by Junyoung Kwak and Tomoki Noguchi and Vaibhav Bandewar. Yep. So first of all, there's some recap on the Q-learning. So Q-learning's basic structure inherits from a Markov decision process, which was not exactly for reinforcement learning, but Q-learning makes use out of it. And Q-learning inherits Markov decision process's memory list property, which basically assumes independence from the past to make in making decisions for the future, which enables reinforcement learning. And Q-learning doesn't inherit the complete knowledge of environment assumption of MDP, which will, in that environment where the agent knows everything, the solution will be solved by dynamic programming. And that's because by nature of reinforcement learning, agent takes a try and error approach to learn about the environment. And Q-learning, another emphasis is that it's a model-free algorithm which doesn't have a function, an estimation function for transition function or reward function. It just it actually takes the action and then gets a feedback from the environment to make get the next policy instead of estimating what will happen if I take this action. So basically, Q-learning is aiming to stop collecting information at an effective but maybe an suboptimal point. It's settling to some point. Okay, so the Q-learning function, basically the equation is as given, which is the first equation is the policy, is trying to get the maximum action, that the action that maximizes the Q value, which is, in other words, action value. And the second equation is saying that the Q value, the action value, is basically the immediate reward from that action to going to some state, the next state, and the future, and the total future maximum Q value from next state. So there's kind of a recursive property there. Yep. So in terms of, there's some, and this is a little bit of extension on the Q-learning. So Q-learning, unlike the previous equation over here in the right, the Q-learning now could be learned by iterative update rule, which alpha here is the learning rate, and it's bounded by 0 to 1, and if alpha becomes 1, then it's exactly the same as the Bellman equation, as you can see over here, the previous one. This is basically just controlling how fast the agent is, how much agent is going to incorporate from in terms of the estimation of the learned value. Okay, and so Q-learning, basically the most simplest way to think about Q-learning is in the tabular form. So naturally, the simplest implementation of Q-learning is using a Q table. The Q table consists of a row, like it could be a row of state and column in action, column of action, and this could be switched. But anyway, and the entries are the Q values, the action values itself. So basically, this Q table is telling the agent which action to take at a given state. So it's kind of like a cheat sheet. But the problem is that as the cheat sheet gets too long, the implementation becomes too infeasible because you would have to store all of the Q values by action state combinations. So since using the tabular representation for the Q value function might be infeasible when it grows, the alternative is to use to approximate that Q value with a function. This is called the value function approximation. As you can see over here, we are approximating the Q hat is basically getting some weight. By using some weight, we are approximating the Q value. So by doing this, we would no longer need, it would take much less memory because we would only have to store the parameters for the function instead of having a huge matrix. Or yeah. And this function approximator is not only confined to a linear combination of features, but that is widely used though. But it could also be decision trees and nearest neighbors, or even neural networks. And the neural network part is basically what we're trying to dig in. So using the function approximate, so using the deep neural network as a function approximator for the action value Q value function is basically what the DQN is trying to do. And as you can see in these diagrams, this DNN, deep neural network, is trying to approximate the tabular representation of the Q value function. So we're basically training this DNN. So first of all, in terms of DNN, any artificial neural network architecture can be used as a function approximator for the Q value function. But CNN, which is what I'm trying to introduce, the convolutional neural network, is widely used as the architecture implementation, as an architecture to use in use as a function approximator for Q value function, especially when images are input. And because a lot of the recent studies in this area are making reinforcement learning are done in like building gaming AIs like Atari 2600, AlphaGo, or AlphaStar, which plays StarCraft. And because the image, for those games, basically the primary source of information comes from the game screen. So that's why the Google DeepMind team selected this CNN, the specific architecture, to best process the image inputs for making a Q value function approximator. And okay, so the CNN's key advantage to over ANNs is that it retains the spatial information, because the ordinary ANN, which we learned during the course, basically has one array, like 1D array, like as x1, x2, so on. But so basically, image input could be 2D or 3D, depending on the color. But this ordinary ANN just flattens it and inputs it. So that's where the spatial information get lost. But as you can see, here CNN uses the convolution to preserve the spatial relationships. So not too detailedly, but so it's basically using a filter, which is kind of could be understood as one concept of some feature, like some feature could be used to detect the arcs in an image, while others could be detected to the diagonal lines or horizontal lines or vertical lines. Each feature has one concept that trying to detect. So it's basically getting the convolutions of these, which is basically getting this small 3x3 matrix, the submatrix of the input matrix, and getting the matrix multiplication, and then which leads to this feature maps. So, and these feature maps could be a lot. There could be multiple feature maps, and this enables spatial relationship. And the CNN is basically training on this filter coefficients, is trying to get it. Like, it's not human defined. It's the CNN is trying to train the weights to get the best filters that can lead to better results. Okay, so the second part of the CNN is that okay, so if the neural network goes deep, there should be some non-linearity, because if it only has linear relationships in the ANN, then there's no reason to make it deep, because basically mathematically the relationship will be the same. Either it's deep or shallow. In an equation it could reduce. So there should be some non-linearity in the CNN, basically to produce a non-linear decision boundary. And first of all, the previous step of convolution was a linear operation. So now we could add non-linearity to the CNN by using a non-linear activation function here, which is used as a ReLU function, the rectifier linear unit activation function. And to just shortly say, it has a nonlinear property, as you can see here, which is getting the max from 0 to x, and the partial derivative of x is 0 to 1, which means that the gradient is either 0 or 1, instead of like a 0.5 or something, like as in the sigmoid function. So the gradient multiplications will not converge to 0 as they multiply more and more, which solves the vanishing gradient problem we observed in the sigmoid activation function as an activation function. And in practice, it converges much faster. So yeah, it has good advantages, but it also has some disadvantages, but there's always also some ways to deal with it. The third key feature in the CNN in terms of feature extraction is the pooling. And so the high level idea is that it controls the overfitting by reducing the dimension of each resulting feature map that we got before, but retaining the most important information, which is also can be thought of as it's insensitive to small translations in the input data image. As you can see in the right figure, these three red small figures have a little bit of small translation, small differences. But in the level of the CNN, the CNN in the CNN version, it's the same as in this right square, as you can see. So this is basically possible because they're getting the maximum or average in the local neighborhood. And max pooling is typically used in CNN because it extracts only the most important features of the data. So that was the feature extraction phase in the CNN. The classification phase in the CNN is that now in the feature extraction CNN, we can preserve the spatial image. Now we just can, for further classification, we can flatten that. Here, the pooled feature that we flatten into a 1D array, and then we use a fully connected ANN structure, which we learned in the course. And then it doesn't have to be one layer, but for like several layers, we can compute the class score using a softmax activation function, which basically is widely used for multi-class classification problems. So yeah, and then as you can see, we can train the CNN using backpropagation for FC pooled and convolutional layers. And since pooled layer doesn't include weights, it could be trained in a specific other way. So the main part, yeah, so we are going to dig into the Google DeepMind's DeepQ network for the Atari 2016, which was introduced as a 2015, which showcased the combination of CNN and Q-value functions successfully. Yeah, so that's why we talked about CNN previously. And the important part of the DQN is that it learns policies directly from the high-dimensional image inputs. And it's called end-to-end reinforcement learning, which means that they directly applied reinforcement learning in training the neural network. So previously it was not like that. They did use deep neural network, but they first processed, like they first feature extracted using the deep neural network, and then on top of that they applied RL, which was like separate, like a two-step process. But here the end-to-end reinforcement learning just incorporates that into one. So that's the important part for this. And also it like did an excellent job in learning given the minimal prior knowledge. Like for example, visual image, as you can see in the screen, or the game score, like which is equivalent to what the human player would only get while he's actually playing the game. And it also addresses some previous instability issues of RL reinforcement learning being combined with nonlinear function approximators. So that's also an important part of this publication. Okay, so the basic DQN architecture is that it defines one's state as a sequence of actions and observation, which means that, because naively thinking, a state, when it comes to a game play, naively thinking we could consider a state as one game screen frame. But here, because the information that the agent can get from just only one game screen frame is too limited. That was a problem. So they kind of broadened the concept of state. No, kind of, you can think of it, they broadened the naive way of thinking about state into a little bit more broader of sequence of actions and observation, which is kind of like virtually inputting a short video of like several frames. And they set the number of frames, which was a hyperparameter, they set it as 4. Yes. And the important part, also the other interesting part, is that they applied one single DQN architecture and a fixed hyperparameters for all tests. Remember that the Google Atari game is not only one game, but like multiple games, like ping pong game, like crashing game, and so on. But they only use one network structure to do that. But by that, they did have to normalize rewards across tasks in terms of magnitude, as you can see. So the training process of DeepQ network is basically minimizing the loss function, as you can see here, the mean squared error, and then by reducing it by gradient descent, aka backpropagation. Yeah, as we learned. And the important part is that by the nature of reinforcement learning, which has the target is not fixed, like unlike the supervised learning setting that we learned, which had perfect labels from the beginning, like not perfect, but given labels. So in DQN training, the target Q value has to be estimated. And Q-learning is also an off-policy learner. I'm not going to dig into the off-policy, on-policy difference too much, but basically this off-policy learner means that the update policy and the action selection policy are different, while the on-policy learner use the same policy for these two concepts. So the off-policy learner, which this exactly means, as we can say, the Q value is estimated by the immediate reward and from that action and the total maximum cumulative reward for the next state, right? And this total maximum cumulative reward is estimate. There's some estimation factor there, and that is estimated by the action that gives the maximum Q value, which is the absolute greedy policy. So this is basically used to update the policy. And it is using an absolute greedy policy, as you can see in this max operator, right? But the thing is that while agent is actually selecting an action, that agent doesn't follow the absolute greedy policy. That's only used for update policy, but the agent uses the epsilon greedy policy to choose his action. And this handles the concept of the problem of exploration versus exploitation trade-off. So because if the agent just also uses the absolute greedy policy as its action selection policy, then it will just could just converge to some local minima too early. It could to some deterministic sense there. But by enabling with some probability of epsilon here, enabling exploration with by probability of epsilon, it could make random actions that are not greedy but could be good in the long run. That could give long run benefits. The part is that in the epsilon, this epsilon in the public Google DeepMind team linearly decrease the epsilon value from 1 to 0.1 during the first 2% of trainings, and then fixed as 0.1 and afterwards. And this means that the agent learns, as the agent learns more and more to the enough point of the environment, there's less need to explore more. We could, yeah. So previous instability issues of reinforcement learning and deep neural network, the higher level idea is that, think about an input game screen that has a 1 time step difference. They might have naturally have a high correlation because of sequential nature. So there is indeed a lot of correlations, right? But the standard deep neural networks, the structures are, the theory is based upon the IID assumption of the input data. But this is not IID at all. So by using highly correlated training with highly correlated samples, it might not have a good conversion behavior. That's the first previous instability issue. And the second one is that comes from the online learning. So online learning is basically a step-by-step learning, can be think of as a step-by-step learning, which means that availability of experience comes at in a k time steps. K could be 1 or more, but anyway, it comes as the experience comes in. Neural network gets trained and discards those used experiences. So naturally, this might have a limited availability of experiences compared to an offline approach that first collects experiences as much as you can, it's complete offline learning setting, and then you start learning. So compared to that, this online approach has limited availability of experiences naturally. And this could lead to a high variance and updates to the policy issue. Because like, you can think this as the variance decreases. We know that the variance decreases as the sample mean more closely represents the population means and vice versa. And this limitation of experiences doesn't necessarily mean less number of samples, but still can be considered sort of as a less representative sample compared to the offline learning that we discussed about. Because of this less representative samples, there might be some more high variance, right? In the update to the policy, update to the weights, which is the policies, right? And this high variance could lead to abrupt changes in the ongoing policy. Remember that the neural network is trying to converge to some good policy, and it could be abruptly changed. And given the non-stationary nature of the data in the reinforcement learning setting, this abrupt changes lead to abrupt change in distribution experience. Because policy determines action, action determines the next data sample, how it looks like, given the nature of RL. And this could, unfortunately, sometimes lead to an unwanted feedback loop, which we will discuss later. And this obviously can lead to divergence of the neural network. The very third instability issue is the correlation between the predicted Q value and the target Q value. So this correlation issue happens when in the traditional setting of training using one single network to get the both predicted queue and target queue. So the first pass will naturally be the predicted queue for this state, and the second pass will be to calculate the target queue, which is basically the target queue here is not the sum of the immediate reward plus the total maximum cumulated reward, but this target queue that's trained the second pass is basically the second term, disregarding the immediate reward. It's the total maximum cumulative reward. Yeah, the target queue refers to that. So the when weights are updated via the gradient descent, the predicted queue will obviously update, right? But the problem is that if we're using a single network, the target queue updates will be also calculated using the same weights, because the absolute weights of that one neural network is already changed by the first pass. So the problem is that the predicted queue, we're trying to move closer to the target queue. We're trying to like minimize the loss function, but the target queue, which is also calculated with the same weights as the predicted queue, is also moving further from the predicted queue in the same direction. So it's basically an escaping from it. So that's called dog is chasing its own tail problem. And this will make the neural network to hardly converge. And to address these issues, two of these issues can be solved by this concept of experience replay, which is basically storing the agent's experience at each time step pulled over many episodes. Episodes refers to the, for example, gameplay, the start of one gameplay to the terminal to the gameplay. That's one episode. And so the experience replay has a replay buffer which stores all these experiences in each time step. Of course, the replay buffer is not infinite, but it's finite. But it's a lot of it could be, the size can be varied, but it could be pretty big as well. So that's the storing part of experience replay, and the sampling part of experience replay is to uniform random sample experience from it to form a mini batch, and then train the weights of the neural network. And the part is that the experience replay requires to be an off-policy algorithm, which is like a Q-learning, and the reason for it is that experience replay is basically aiming to learn, like in terms of evaluating actions from previous experiences that were generated by many old policies. It wants to also learn from old policies. So, but the on-policy algorithm, as we discussed before, assumes a single policy that governs both update policy and the action selection policy. So it doesn't really match with what this experience replay is aiming for. So the Q-learning, which has separate policies for its updating policy and action selection policy, can go well with this experience replay. So the first advantage is the greater sample efficiency, which is basically instead of throwing the data, the samples immediately after use, like basically after collection, they train upon it and throw it away. They don't do that here. They just, now the samples, since they are being stored, the samples can be reused multiple times for training. So there's and they don't really, in the replay buffer, they don't just discard the experience, and they only discard when the replay buffer size, since the replay buffer size is fixed, incoming new experiences will kind of pop. We will kind of make the old ones go out. Like, unless that happens, the replay buffer really doesn't discard the experience right after using it. So that means that one experience can be reused multiple times for training. So there's, first of all, there's a greater sample efficiency in that approach. And actually this property of reusing experiences gives another advantage. which is that first of all, neural network has a tendency to forget about the experience that's not currently training with. This is called the catastrophic forgetting problem. Like, for example, if an agent's trying to learn how to walk near a cliff, the agent could fall off a cliff, which is an experience that will give the agent a negative reward. So it will train the neural network not to go to that direction. So for a while, the agent may not fall off the cliff, but because this is epsilon greedy approach, like it could, by some random action that it took, it could again fall under the cliff, despite that it learned how not to fall off a cliff previously. So this is an issue of forgetting. But by reusing past experiences, agents could again use the previous experience of falling off is to remind itself that it's and train itself to not fall off the cliff again. So that solves that forgetting issue. And it also resolves the instability coming from the training with highly correlated subsequent samples, which means that, yeah, obviously by random sampling, training data will become more IID-like, like as in the supervised learning setting. So it will naturally converge better. And it also resolves the instability coming from the online learning. So before we talked about this unwanted feedback loop that could be stem from the online learning problem. And it's basically, here is a good example. Like, so let's say that policy A gives the experience of X, and training with this X creates policy B, and policy B gives experience of Y. Training with Y gives policy A. So there's a loop here. So this means that the neural network will not hardly converge. So, and this is mainly because in the reason the online learning step-by-step limited availability of experience issue, X and Y might not be available together, and that's why this loop, unwanted loops, could arise. But using the replay buffer, which has a more broader availability of experience at the time, replay buffer could contain both X and Y. So it could avoid falling into the loops. It could just train X and Y together. And that's the contains both X, yeah. So this could, by doing this, it could avoid the loop by training them together. And the third problem can be solved because of the fixed Q target issue, which is basically, instead of training the predicted Q and the target Q value with the same neural network, it now uses two. So in terms of architecture, the two networks are exactly the same, except for that the target network uses frozen weights from the predicted Q network. So for every C iteration, the C being a hyperparameter, weights learned in the prediction network are copied to the target network. And at first, the weights were initialized as the same. And basically, so this, in the equation, this minus superscript over here denotes, says that it's a frozen target network over here. Yeah, and basically we're, again, trying to minimize the loss function. So the advantage of this is that it resolves the instability coming from the correlation between the two values, two Q values, because as obviously as the target function gets fixed for a while for the time of C, more stable learning can be possible. So now the target Q doesn't really escape from the following Q, approaching predicted Q, but it could lead to some kind of, the predicted Q now could move closer to target Q in terms of reducing the loss function. And yeah, it could be confusing, but the thing to remind is that the target network calculates the maximum Q value for the next state, not this including everything. So putting this all together, like this, basically the pseudocode for this deep Q learning with the concept that we learned. So here, as you can see, epsilon gradient policy is being used, and here basically the experience replay, the storing and the sampling mini batch is done over here, like in the same for loop, which the for loop, the outer for loop is for multiple episodes from the, for example, in the game, the starting of the game to the end of the game, and this is for inner loop corresponds to each time step in that one specific game, and then they are doing these in the same inner loop. And then as you can see, the frozen weights, the target networks calculating the target value with the frozen weights, and then DQN training, and then every C steps target network, like the predicted Q network weights, the learned weights are cloned, copy and pasted in as the target network's weights after C iterations. And yeah, that's all for the presentation.